Our next speaker is Dr. Mari van Wyk from the Northwest University. During her tenure as consulting statistician at the Department of Statistics and resident biostatistician at the Focus Area and Center for Human Metabolomics, Dr. Mari van Wyk has encountered all sorts of study designs spanning the phycological to the biological, in vitro to in vivo, plants to animals, and urine to breast milk samples. So she has tackled quite a lot of data produced by a variety of samples and produced by a diverse measurement set of instruments, from questionnaires to targeted and untargeted GC, LC, and NMR. In her talk, she will then share with us some of the tricks of the trade, specifically when it comes to valid research in metabolomics. Over to you, Dr. Mari, and thank you so much for availing yourself.
Thank you, Aurelia. I hope you can hear me.
Yes, I can.
Okay, I'm going to start sharing. You will let me know if you've got any difficulties.
Okay.
Okay.
Yes, I can see your screen.
Okay, awesome. Thank you. Okay, welcome everyone, and thank you for joining this talk on validation. Like Aurelia said, my name is Mari van Wyk, and I am the resident statistician at the Center and Focus Area for Human Metabolomics. Today, I'll be sharing with you what I do on a daily basis to help ensure that we produce valid results. This topic was specifically requested, which I find quite exciting because the validity of findings is a very relevant concern. So let's get started. Okay, first off, why is validity an issue? Okay, so much like the complicated relationships between a dog and a newspaper, never knowing whether it will whack or reward you, metabolomics results can be so promising but so elusive. And the field has unfortunately become notorious for not being able to reproduce results. And the primary reason why, I believe, is because metabolomic studies lack statistical power. Sample sizes are too small, the number of variables are usually far larger than the number of cases. We're often looking for very small changes, and changes are overshadowed by the busyness of the human body, for example. And we can then become optimistic Santas looking for a gift during load shedding. Okay, so why is a lack of power such a concern? Underpowered studies can lead to false discoveries. So this may seem a little bit counterintuitive. If the effect is present, even in a small sample, then it must be real, right? Well, in some cases, such as inborn errors of metabolism, the effect is so dramatic that you can say that. But usually there's additional validation, let's say genetically or so forth. When we rely only on the data at hand, and repeatedly so, it becomes more and more likely to eventually find something that looks significant. And hopefully, if there's time later, I'll demonstrate this to you. Okay, but it may be whatever you find that's significant may only be a glow-in-the-dark unicorn, and it gives you false hope. It's like ESCOM trying to fix the problem. Okay, so if we know that our sample sizes are too small, why do we keep sampling small? It's often difficult to recruit participants, as all of you know, I suppose, and you may be investigating a rare disease. Participants may be vulnerable, let's say you're working with children. And so we tend to opt for a low number of participants, or we end up having no control group. Sample analysis is also very expensive. And sometimes the matrices we're interested in are invasive to get. So that's probably the best example would be CSF. Okay, so this tempts us to draw conclusions that are far beyond the capability of our data. It's like this thrifty groom that you can see in the comic. Other characteristics of studies are also making your researcher's life very difficult. The data sets are big, especially when you're performing untargeted work. The natural variability is large. Individual metabolisms differ from each other, but individuals differ within themselves as well from one moment to the next without even having a major intervention of some sort. Because of the difficulty doing research on humans specifically, we tend to squeeze every last drop of info from whatever samples we do manage to get. But then we might end up squeezing random, inconsequential bits of info out as well. And that is a big concern. Okay, so this is just a brief excerpt from a publication by Sasanti, which shows what the sample sizes should look like when you're just performing a standard PCA. And it's quite scary because I know most of the studies that I dealt with is nowhere near what we see here. So it comes down to being reasonably close to the true loadings. It takes about 50 cases given 50 compounds and about 150 cases given 1,000 compounds. So you can place yourself somewhere on that scale, because this was very crudely deduced. So please read the publication, but it was kind of an eye-opener for me. Okay, all these difficulties and more lead to what, Donna, sorry, there's some surnames on this page that I'm going to struggle with. That leads to the conclusion that most research findings are false. That's literally the title of the publication, which is kind of scary. So some of the authors that followed were jumping on the bandwagon, others were a bit more optimistic, but it looks like the final say is still that most of the findings are false. Okay, so if you weren't feeling depressed before that slide, you probably are now. But I want to side on the more optimistic and say that a little replication and a little bit of planning can go a long way. And that's what we're going to focus on today. So how do we go about this? Make sure you have the best study design possible. Make sure there aren't any obvious errors in your data. As far as possible, you have to be error-free. Cross-validate your findings as far as possible. And very importantly, be conservative with how you generalize your results. So do the best you can and do all you can. So when should you consider validity? When should you be concerned about validity? Well, before you collect your samples, before you analyze your samples, before you analyze your data, and after you've analyzed your data. So essentially throughout the entire process, this should be a constant concern and a matter that you want to address throughout. Okay, I'm a bit pressed for time, so I'm going to reverse the order in which I present. I believe you'll be more interested in the data and results validation. So I'm going to focus on that. I also focused a little bit more on using Excel because there's a little bit of flexibility there, which you don't really get on the online platforms as much. And it's also, I don't know, it's a tool that people feel comfortable with if you're not comfortable with the scripting language. Also, there are very detailed resources available for Metabolomics specifically, and these explain the functionalities a lot better than I can in the time, and I can make these resources available to you. Therefore, so the first part of this talk will focus on evaluating and improving the quality of the data you generate and the validation of the results, the statistical results at the end. And then if we've got time, we'll look at experimental and measurement design. Okay. So before you're performing any data analysis, you have to validate the data, check the data. So what I'm going to touch on today is some basic error handling, how to use the data from your QC samples, understanding outliers, why metabolomics data requires scaling, and how, and more importantly, when to address missing values. First up, error handling. So I do have a demo set out for you here, but again, if I'll dive into this if there's time, or if you can sit with me through the break, then we can run through this demo. But in short, make sure your IDs are unique in two ways. You should have two IDs essentially, one that uniquely identifies the sample and one that uniquely identifies the case. This is necessary if you've got something like repeated measures. Now, these things seem obvious, but people don't do it and it leads to havoc. Okay, so make sure you don't have merged cells, make sure you don't have double headers. Check the decimal separator if you're working in Excel. So if you go to the advanced options in Excel, you have to make sure that the full stop is your decimal separator and not the comma. If you set it to the comma and you convert to a CSF, you're going to have trouble. It may incorrectly assign values to the wrong columns. Okay, check that the numbers are actually recognized as numbers and not as text. Otherwise, if you pull the data into something like Metabolomics, it will reduce it to missing values. On that, check that your zeros are set to missing values if that's what your software requires, and then count the number of missing spaces that you've got or the number of zeros that you've got, so that when you import your data, you can make sure that there weren't any numbers that got lost during your import or your upload. Okay, check for duplicate rows. And check the counts. If you know there should be 20 cases in a group, check that you've got 20 cases. Check that you've got 20 unique cases. Then it may be also necessary to simplify your variable names or even your case names. So what I always suggest is to replace your complex variable names, especially in untargeted metabolomics, where the names become very long and there's very strange and weird characters in those names. I would, as kind of like a first step, replace that with just a number system, so V1 to V500, for example, and then have that single reference list before you even start prepping your data and removing variables, so that you've got one reference list for your entire study. Now, this all seems very simple and straightforward, but people forget to do it, and it creates havoc. Right, QC. What do you do with your QC data? How do you know if your data is of acceptable quality? Okay, so the QC data that we gather allows us to quantify analyst and instrument repeatability for each compound using something called the coefficient of variation. Compounds that could not be measured repeatedly are usually considered unreliable, and you should either adjust or remove them. Okay, so the lower the QC, the better, but I want to share with you some rules of thumb that we use. So we use a 50% cutoff for untargeted work and the FDA guideline of 30% for targeted work. And this is then, of course, if you're looking at CVs across batches. Obviously, if it's within a batch, I would reduce that. My rule of thumb is usually 15% for targeted and 25% for untargeted. If it's above this, you have to correct or remove your compound. Okay, just a quick recap for those of you who may not be familiar with the coefficient of variation. The CV is calculated as a ratio of the standard deviation to the average. And in the QC setting, the CV conveys the instability of the method. Okay, univariately, the CV works really well. You can look at problem compounds and you can adjust accordingly. Multivariately, it's a bit more complex, and you have to look multivariately in the metabolomic setting because that's what you're doing. You're looking at the global metabolism. Okay, in the multivariate context, you can only actually assess the general acceptability. You can do this by constructing a PCA like the one I've got here, which your two groups or your grouping indicator is the samples, your experimental samples, and your QCs. And this gives you a nice visual way of evaluating the biological variation, that's the spread of the samples, against the analytical variation, the spread of the QCs. So if the biological variation far exceeds the analytical variation, then you're good to go. But please check that the total percentage variation explained by the principal component scores plot you're using is at least about 50%. Okay. I combine, sorry, I'm saying okay a lot. I combine the univariate and multivariate approach. Now, what do you do if your QCs look bad? Okay. Depending on the type of QC and the severity you have to either exclude or adjust your compounds. I mentioned severity because I don't like to adjust compounds that vary too much. I would rather exclude them. So there's a little bit of subjectivity there, but if a compound varies, if the CVs are like above 100%, which I've seen, then I would not adjust because it's just too variable. Okay, so after any exclusions or adjustments, you need to reassess to see if your approach works. Okay, there are two main sources of variation to adjust for. That's the drift, so how the instrument kind of deteriorates or becomes less sensitive as the batch moves along. And then there's obviously shifts between batches due to all these environmental factors and whatever else may have happened to the instrument in the meantime. So you can use QC samples or whatever fancier approach is available. I know Metabolist has a couple. I'm not going to discuss that, but I will mention that the batch content must be the same across the batches if you're using Metabolist. So let me show you the basic idea described in the Van der Kloot paper, which I'm referencing here, because you can do that in Excel and it's very intuitive. So the basic idea is that if you have a deteriorating sensitivity within a batch, you can see that's for batch 1 and batch 2, and these are the QC samples for a specific compound. If you have this deteriorating sensitivity, they give you a nice little formula which allows you to correct for that, and you end up removing the drift. Okay, so you can read up on the publication, and you're welcome to email me or contact me if you've got any questions. I just want to go through the basic idea. Right, so once you've got your drift sorted out, there's still this shift between batches that you also need to correct for. So that's the second step in the correction, and they also provide information here. What I want to, well, then maybe let me wait for some of the examples. Okay, so that sounds great, that looks great, but that's a very optimistic picture of how to correct for QCs. So just to get you a little bit upset, here are some real life QC examples that I've encountered. So in this specific example, there were a couple of issues. So there was a bit of human error. So we had a little bit of QC prep that went haywire. So that was our one problem. And then the second problem was the planning wasn't done sufficiently. So we ran out of QC and we had to reconstruct a second QC. And obviously the difference between the first QC and the second QC sample was quite dramatic. So this was a big problem, and we corrected for it by correcting for considering this is a batch, and then we, in some instances, depending on where the outliers fell, we removed the outliers or the outlying QCs before using them in correction. And so there was a combination of approaches that was used here. But the point I want to make is that you need to trust your QC. So plan your QC carefully and prep your QC carefully, because it's the only way you have of correcting for variation that's unwanted and not having to remove a compound completely. So this is just to demonstrate that if your QCs fluctuate a lot, then if you want to remove drift, so this is the drift we observed within a batch, then be careful what you select as your drift correction. So the basic approach is just to use this straight line, this linear correction over here. But as you can see, that may induce more error than there was observed in the first place. And so you can fit more fancy models if you prefer, but I would be careful. So that's why I say treat QC correction with care, because you can induce more error than you're trying to remove. Okay, then like the previous slide said, once you've done any correction, you have to check it again. You can't just correct and continue on with your life. So this scenario was unfortunate, but true. So the QCs, it was a pooled QC, and the QC didn't have sufficient power. I presume it was due to a dilution effect by pooling that had the effect that even though the shift in the batches was removed in the QC samples, so there you can see we could get the shift between the batches out in the QC samples, that correction didn't pull through sufficiently to the actual samples. And so you have to bear this in mind in your statistical analysis to say, yeah, so maybe add the batch effect as one of your factors. Right, so this is my go-to route. If at all I want to avoid any correction. If I do correct, I want to do small corrections, and I want to make sure that I have a pooled QC. This is very important. So your QC must be representative. You can't use a QC that doesn't look the same as your samples. That's going to induce a lot more error. And then if you want to do a double correction, so in other words, within a batch and between a batch, be very careful and check, make sure everything looks good. So in this instance, and hopefully we'll get to that, so in your experimental design, if you're expecting a lot of variation and you're expecting to use your QC samples to do corrections, then I would suggest that you repeat selected samples so that you can see that your QC correction was successful. So rerun the same sample in different batches, and then once you've done your correction, you can compare these samples to see if your QC correction was effective. Right, outliers. Okay, so before I even try to detect outliers, I consider the group sizes. If a group has 15 or less cases, I do not look or remove outliers. In metabolomic studies, which are multivariate, you should remove cases based on their entire data vector, so all the information you've got. So I prefer to use a PCA scores plot with a 90 or say 95% confidence interval. That's the same as what you can use in Metabolite Analyst. But again, make sure that you've got sufficient variation explained. You can also use cluster analysis. I'll show you some examples just now. In Excel, you can consider scaling and summing observations. I've heard of people doing that, and detect outliers using the interquantile range rule, which is basically the box plot rule. But I would tread carefully here because your compounds are usually measured on different scales. So the orders of magnitude differ quite a lot. So you have to make sure that they are all treated equally. So your scaling needs to say that they all contribute equally to this sum that you may want to use. Also, tread carefully when you've got repeated measures, because you're looking at changes within the individual. If there are outlying observations there, I would rather look at it for the specific statistical analysis that you're trying to do. But actually, I would preferably not remove outliers and repeated measures. Then lastly, always try to figure out why the case looks different. Was it just analytical error? Can you maybe rerun your sample, or was it clinical? It's always, the reviewers are always on your side if you can provide additional support as to why this case should be removed. Okay, so here's an example for PCA for outlier detection. So again, look at the variance explained on your axes, make sure this is about 50% or at least 50%. And then depending on how repeatable you expect your samples to be, you can set your confidence interval to 95, 99 in this instance, or 90. I would not go below 90. You can also use cluster analysis. So here's an example where you can clearly see the purple star is completely removed from both groups. So there's something definitely going on there, and I would not hesitate to remove the purple star. But in the figure on the right, you can see that that green star is different, but not so different from its originating group. So here I would try to find another support, maybe if it's out on the PCA as well, or if there's some clinical reason, then I would remove. Right, and this is just if you've got the sum of all the compounds, scaled sum. If you want to use the interquantile range, then you can basically use these rules of thumb, 1.5 times the interquantile range. So basically a box plot, and if it's above the I-beam, I call it, then it's an outlier. Right, scaling. So why do we need to scale? We need to meet the assumptions of statistical methods. So this is important. People kind of set assumptions aside a lot, and I know most of the statistical methods are relatively robust, but we should not chuck the baby out with bathwater. Violating these assumptions produce unreliable results. It means you cannot trust your p-value. Okay, so the purpose of transformation is to correct for skew data. So in metabolomics, we often have a lot more small observations than large observations, so the data is skewed, and you can correct for that usually by doing a log transformation. You also need to place the variables on equal footing. So the smaller peaks are not necessarily less important than the bigger ones. But mathematically, the bigger peaks with bigger, higher concentrations will be considered more important. And so we scale to place them all on an equal footing. So most of us have this kind of we log and auto scale, and that's kind of the routine that we use, and we no longer really fiddle about when it comes to transformation and scaling. And I want to challenge you here by referring you to this publication. Now, it's not a very recent publication, but it's still very useful, where the matter is discussed in some detail. And what I love about this paper is this table that it provides. So you can see the various methods of scaling, how it's calculated, and then most importantly, the aim behind the transformation, the advantages and the disadvantages. And I want to challenge you to go and look at this table and decide, not necessarily based on what your graph looks like in Metabolomics alone, but also consider the advantages and disadvantages and what you want to achieve through your scaling. Right, missing data. Okay, so missing data results from various combinations of sources. It can be the sample, meaning that the compound really isn't in the sample, or it can be analytical, you just couldn't detect it, or it could be an alignment issue. So it's a misalignment and now it's set to missing. And then there are various imputation methods. So you can simply remove variables where the missing data is just too much, but remember to look at the groups. So in other words, if something is completely missing from one of your groups, but present in the other group, then it's obviously important. But if it's basically missing from all the data, all the groups, then you can remove it rather than impute it. That would be my go-to rule. And then the Metabolomics usually provides options in terms of replacing based on the samples surrounding the missing value. I prefer not to do that because I believe it's usually the limit of detection or absence in the sample that produces missing values. So I like to replace based on the minimum observed value. So Metabolomics has the option to replace by a constant, and that's kind of the rule of thumb that I think most of you know, where you replace by half the minimum. That's kind of a stock standard rule. I believe there's a little bit of a better way to do this, and if we have time, I'll demonstrate it in Excel, because I think it's better to replace it with a small random number rather than one fixed number. And if we've got time, then I'll explain. Right, so missing values, when you replace missing values is rather important. So for instance, CVs are, the coefficient of variation is affected by low averages. So obviously if you've got missing values or a bunch of low values or whatever, then the CV will inflate. Again, also in the QCs, if you've got a lot of missing values in the QCs, you should not necessarily impute there, because if there's not data in the QC, you cannot use the QC to correct. So the proportion of missing values when you impute the missing values and how you filter out what variables can be reliably reported it depends very much on your data set. But pay attention to the percentage of missing values is basically the take-home message. So how I order the events usually depends a bit on the results, but usually I would remove compounds which have a lot of zero or missing values in the QC samples. Then I would also remove those compounds that were not detected in the samples across the group. So meaning it's not just one group that's missing, there's missing data for samples across all the groups and more than 50% of them, for example. And then only I would impute, and then I would perform my quality assurance to check if the data is of a sufficient quality, and then perform adjustments as necessary. Okay, finally, how do you validate your results? Specifically, when you do not have a separate set of data to confirm your findings. So ideally, you want a large data set. You want to be able to split it into a training set and a test set. So the training set, you get your initial results, and then you confirm that result by using your holdout sample or your test set. So as we've discussed in the very beginning, we usually just don't have enough sample to achieve this. So what do you do when you don't have a holdout set? Okay, so I'm going to look at this in two ways. I'm going to look at it in the univariate setting and then in the multivariate setting. So in the univariate setting, we're going to look at specifically p-values, their pros and cons and limitations, and then the steps to support p-values. So correcting for multiple testing, effect sizes, and plotting your data. Okay, so the p-value is the probability of the observed result plus a more extreme result if the null hypothesis is true. That's the formal definition. The more practical interpretation is that it's the likelihood that any observed difference or effect, or a bigger one, is simply the result of random sampling, right? So if you were to draw a different sample, you would get a different result. And hopefully I can demonstrate this to you in Excel a little bit later. So it's just the probability of getting a difference or an effect by chance. So obviously if the p-value is small, then the chance of this being just a random event is also small. Okay, so in research, this whole idea has been blown up disproportionately. The p-value has been seen as good as gold for a long time. So if a p-value is small enough, it can't be random noise. So it must be a legitimate finding, right? No, unfortunately not. The correct interpretation of a small p-value is actually simply that the experiment is worth repeating. It is not conclusive proof that the difference or the effect exists in the population, nor that the difference has any meaning. So hence the sad face. Okay, so the p-value has come under pressure, and some of the reasons why is study designs often don't sufficiently incorporate confounders. So these confounders are third-party variables that are actually responsible for the effect but weren't measured. So the p-value won't know about that. Okay. Then, as we've said before, inappropriate sample size, but not only too small, also too big. If your p-value is too big, it's also a problem, because then by default your sample size is too big. Then that's also a problem, because the p-value is inversely related to your sample size. So the bigger your sample size, the smaller your p-value, regardless of the effect. So it's the flip side of the coin is also true. And then the p-value can detect the effect, detect effects of no real importance. So there's no effect size related to it. It's only used to establish whether it's beyond chance. So it's quite limited. So there are a couple of things that we need to consider. The first thing we need to do to support or validate, bring more validity to our p-values is to correct for multiple testing. So especially underpowered studies can lead to false discoveries. Repeatedly testing different effects using the same data is more likely to eventually give you something significant, but purely by chance. This is why correcting for multiple testing is very important to validate your results. So MetaboAnalyst corrects by controlling the false discovery rate. I think it's the Benjamin-Hodgberg approach, but in any case, you can go and read up on that. But you can also correct in Excel with a very simple formula known as the Bonferroni-Holm or Holm-Bonferroni, whichever you prefer, approach. It's a little bit more conservative, but it's easy to do in Excel, and sometimes it's a useful trick. I have a little recording of that, so if you don't get it, I'll send you the video. Okay, then effect sizes. So Jean Glass said that statistical significance is the least interesting thing about your result. You should describe the result in terms of measures of magnitude, not just does a treatment affect people, but by how much does it affect them. So effect sizes are key to what we do here. Study design and data analysis. Unlike p-values, they are comparable across studies, and they're actually independent of sample size. You'll see in the formulas I'm going to show you that the sample size cancels out. Okay, but always the but. You still need to have enough samples to at least accurately estimate the mean. So this doesn't, I just want to full disclosure, better sample size is always, a bigger sample size is always better. These are just ways to assist you if that's not possible. Okay, so effect sizes are dimensionless numeric measures. They can be calculated from your observed data. They are used to quantify the strength of findings. That is the relationship between two variables. So let's say cured or failed and so forth. So it's the strength of the magnitude of the difference. So just my little joke here, of course size matters. Who wants a small glass of wine? Okay, sorry, let me skip forward. Okay, so here we've got a table of effect sizes. Here's the reference on the left. And you can go and explore this reference. So you can see for basically all analyses that you want to do, you can get an effect size. And these are the calculations that you can use. But most of the software packages will calculate this for you. The one thing that I would critique Metabo Analyst on is to say that they only have fold change as a measure of an effect size, and I don't like fold change because it doesn't take the standard deviation into account. So I would suggest that you calculate in Excel Cohen's d. It's a simple formula, although it doesn't look like it here, but if you read the publication, you'll see that it's a straightforward calculation based on the mean and the standard deviation. Okay, sorry, I see I've still got some voiceovers popping up in between. All right, finally, you should plot your results. What I like to say is that you can go through all the work of selecting your important compounds, but at the end of it, if you have your list of markers or whatever you want to call them, if you draw a box plot of those markers across your groups, you should see something. If you don't see something, something went wrong somewhere. So at the end of it, plot. And I like these box plots specifically because they show the specific individual observations. Those are the dots. So you can see here in this example that even though there's a massive difference between the first group and group 2 and 3, there were still some individuals that would lie perfectly or fit perfectly well into the green group as well. Okay, so how do we validate on a multivariate level? First off, you have to look at the performance. Then you need to do some validation. So we said we don't have a test set, but that would be ideal. Otherwise, you can start leaving samples out and see what happens. And then last option is to look beyond, look whether your model or your result is beyond chance, and that's why we use permutations. Okay, so first off is the performance. So here, your effect size would essentially boil down to a separation of the scores plot, for instance, if you've got a PCA, combined with the variance explained on the axes. And then if you've got a PLSTA or a predictive model of some sort, then you would look at the prediction accuracy. But check that your prediction accuracy is not skewed to one group. So let's say, for instance, you've got a very unbalanced group design where you've got a lot more healthy controls than you've got sick individuals. Then obviously, purely expressed as a percentage, if you can just classify all of them as healthy controls, then you would be 90% accurate. But that only means that that's only a reflection of the small proportion of sick individuals rather than the actual accuracy of the model. Right, so you have to start leaving out some samples. So at the very lowest level, you can just test the stability of your model by leaving one sample out. So this has been critiqued in the recent past, saying that it's too it's not conservative enough. It's too friendly. So I would not call this validation. I just call it checking the stability of the model. So meaning that if I leave out a single case and I redo all my stats, what changes? And if I keep on doing it, leaving out one case at a time, how much does my result fluctuate? If it fluctuates too much, my model is unstable. There's instability in the model. And that makes it invalid, sorry to say, but it's then invalid. If you've got a larger sample size, it's better to leave K out. So instead of leaving one out, you decide you want to leave 5 out or 10 out and so forth. Right. So why do we want to hold out samples? Because these models tend to overfit, especially something like PLSTA. It's well known, it overfits, meaning that it works perfectly for your data set, but on all the other data sets, it doesn't work or repeat at all if you redo the study on a new set of samples. And this obviously is detrimental to generalizability. So how do you do this? Like I said, you can do the full validation or a low-level validation or just check the stability. Lastly, you want to check that whatever result you've got is beyond chance. And for this, we use permutations. So what you essentially do is you construct a distribution of possible models. So you break your group identities. You randomly assign cases to groups. So you're breaking the group structure, and then you build your model and you get your performance for that model, that distribution. And you then plot your actual model's performance against that distribution. And if it's out to the side, in other words, if you've got a small likelihood or a small p-value, which is what a permutation test generates, then it means that your model is beyond chance. There is information in the structure of the groupings, and therefore, if you break the grouping, it falls away or to the side of the distribution of just randomly grouping individuals. Okay, very importantly, only if the performance justifies do you check stability, and that's at the very least. So obviously, if the performance of the model is terrible, there's no use in validating it any further. Well, there may be, but let's, for simplicity's sake, say there isn't. And then at the very least, you need to do a leave one out analysis. Preferably, like I said, a leave more than one out, or in addition, a permutation test. Okay, I'm not sure how we're doing for time, Aurelia. Should we break now?
I'm gonna take some questions. I think we've assigned time for you to speak until 11 for this first part of that. I know there's some stuff you said you wanted to show in Excel. There's a video that you want to share, and then if you can maybe just please post your email address in the chat section. Just to all our speakers that follow after Dr. Marie, our delegates have asked that you at least show your face at the start of the presentation, just because they would like to know who you are in case they do eventually meet you one day. Thank you for that, Marie. So I'm going to take the first question that I have here, Marie. It's from Dr. Shane Mason. It says, hi, Marie, if the PCA explained if that variance is less than 50%, he's asking, should outliers not be removed if that PCA explains less than 50% of the variance?
So no. What it boils down to is you will have to look at more components. So a 2D or a 3D only takes into account the first 2 or 3 principal components. So that's why what we use in-house is the Hotling's t-squared statistic, because then it kind of summarizes up until the nth PCA. So we continue including principal components 1, 2, 3, 4, 5, how many ever, until we've reached that 50% goal. And then we combine the information of the scores plots on all of that. It's just visually, it's very difficult, obviously, to show more than 3 dimensions. So we compress that down into a numeric value with the Hotling's t-squared, and then we use that to remove outliers.
Okay. Dr. Mason, I hope that answers your question. I don't see any further questions. Is there anybody with a question who would like to unmute their mic and ask it directly? Okay, so at this point, Dr. Marie, I think we still have some time. So if there was something specific from this presentation that you actually wanted to show, I think you mentioned something on Excel. You can go ahead.
Okay, I was wondering, I don't know how we can do a quick poll. Do you want to see the Excel cleanup, or do you want to see the correction for multiple testing? What's your preference?
Just repeat that again.
Do you want to look at how to do corrections for multiple testing in Excel, or how to clean your data in Excel?
I think let's start and clean the data first, and then we can do the testing. So it's 10:40 at the moment. You have time until 11 for this part of this talk.
Oh, okay, no, that's not. Yeah, I rushed through. Now we have more than enough time. Okay, can you see my Excel?
Yes, I can.
Okay, can I switch off my video again? I'm a bit jittery on the.
Yes, when you present, feel
breaking up a bit, so I'll start again at the end.
Yeah, when you present, feel free to remove the video. I think it's just in the beginning, just to say hi.
Okay. All right. Okay. So what I've got here, sorry, I just want to move my mic a bit.
While you set up, just a question from Prof. Kromati. Would you allow for him to reuse the stalk for his postgraduate students to point out all the things that they usually miss during experimental planning?
It's not really recorded, but oh, it's recorded here. Yeah, I don't think it's a problem. I'm not sure if it is, but I'm not from my side. I can present it to them as well. I don't mind.
Yeah. So we will also post the recordings on the YouTube channel of Metabolomics South Africa as well.
Oh, okay. All right.
Yeah.
But no, he's welcome to. I can, like I say, I can present as well, and they can ask some questions. Okay, so what we've got in front is I lose momentum when I see a data set that comes in looking like this. But this is typically what you get directly from the instruments. So what we've got here, and this is all fictitious data, I just wanted to demonstrate some of the things that we want to fix. So here's our to-do list on the right. So what we've got is we've got the month in which the sample was collected or analyzed. It's not important at this point. And then the name of the sample, which is some information in it, which I'll get to now. And then you've got your compounds, but it's got the whole, can I say, additional information required by the system. So it's a serum sample, and this is the result. Okay, and then you've got the calculated concentration and the area, which is also exported. And let's say for the current purpose that we need both the calculated concentration and the area. Okay, so how? Okay, other issues that I can spot immediately is these little green triangles in the corner, which basically says, if you hover over, that the number in the cell is formatted as text. So it's not seen as a 0, it's seen as a text 0, as a O basically. And then you can see here that there's the separator used was a comma. So this is rather messy. So how do we fix this? So let's go down the list. The first thing I want to do is I want to fix the columns. So if I go insert, then what I would usually do is, okay, well, first off, I am not interested in anything beyond the brackets. So wherever I have a space, a bracket, whatever comes after that, that's what the star is for, I want that gone. I'm not interested in that part of the name. So if I say replace all, then that disappears. Okay, so that messiness is gone. That's the first thing. Then there's some information that needs to be filled. So I'm gonna, this is obviously I can just drag across for now, but that's not a useful trick. So let me show you a useful trick. So what I do is I select these blank ones, and I want them to be the same as the preceding column. And then I would say, with all of these selected, I would say equals, and then I use the left arrow to do that. And then I say Control Enter, and it fills the formula across the selected cells. Nifty trick. Okay. And now I want to combine this information so that I have unique variables. So I would use the concatenate function, and I would say I want that part, and I just want to underscore in between, and I want to use the description over there. Right. So those are my new variables. These are the names that I'm going to use going forward. Now remember, these are all functions, so you have to say copy and then paste as numbers. Right. And then essentially I just want to move these up because these I want to retain for now. And then these I can delete. Okay. So that's the columns that we fixed. We filled some of the information. There's some more information that I want to fill, but I want to use a different approach here. So what I want to do is select everything here. And then, or just, you can basically do this. I'm not sure if it's going to work. Oh, no. So sorry. So you can use Shift End or whatever you want to do, but just select the entire column where you want to replace your blanks with whatever it should be filled in as. And then you go to Find, go to Special, and you say, I want to go to blanks. And then it selects all the blank cells for you. And we do the same trick that we used previously. And we say equals, and instead of left, we use the up arrow, and then say Control Enter. And then it fills it down for you. Again, you need to paste as numbers. Okay, so now our columns, happy with the columns, let's look at the rows. So we've got a name here. So this name is rather cryptic. So I know a bit about the study. I know that S indicates the sample. So there's one, or subject, sorry, not sample, subject one, and then there are 2 time points for these subjects. So this is problematic because I need an ID for the sample, but I also need an ID for the person because it's repeated measures. All right, so I use something called the mid function here. So I want to just get the first part of it. So I say that, and I only want to keep characters 1 to 2. No, sorry, I'm switching it around. This one should be here. Okay, so subject. So you can see I have extracted the subject part, and now I want to extract the time point, so the sample, specific sample. So I do that, and then I start at 3, and I want the 2 characters from position 3. So it's S would be the first, 1 would be the second, and then T is the one we want to start at. So that's position 3, and we get 2 digits from there. Right. Okay, so that's that. Now, so we've done all of this. I'm happy with the layout. That's done. Now, I want to start looking at the numbers, that this messiness going on here. Okay, so the first thing I want to do is remember I said check the decimal. Now it's a very simple thing, but it really can create such havoc. I've seen, you can ask maybe some of the people that are listening how the simple setting just confuses everyone, and you get different results on the exact same data set just because of the setting. Right, so you go to File, Options, and you go to Advanced, and you'll see here there's something called Use System Separator. Now, when you install Excel for the first time, or a new version of Excel, or maybe even just an update of Excel, this is selected, and the default system separator is a comma. So usually this is what your would either look like this, use the system separator, and then the other option is that it would look like this. You don't want that, because what is a CSV file? A CSV file is a comma separated file, and that is the file that you need to upload on whatever stats, online stats program that you're using. So it will confuse the decimal separator with the column separator, because both are commas. So we make this a dot, and we say, or just a full stop, dot, and say, okay. So now we know that the background is set up right. So, but this is still imported as some form of a text. So this is still messy. So I would go Control-Shift-End, make sure I can, oh, sorry, usually works, but okay, I don't want to select that. But okay, you can use Control-Shift-End for a big data set, and then you can select all your numbers. And now what we want to do is, the first thing is we want to say, find replace, and we want to replace the commas with dots. Replace all. Okay. Now you'll see that this looks like a number, but is it really a number? So now you have to select, and this is an important trick. I don't know why Excel is gremlins, but in any case, you have to select the entire column. Don't do this and set to number. Select the entire column. And then at the top here, instead of having general, select number. Now you can see that some of them were converted to number, but not all the zeros were correctly converted to number. So what now? So you can select this again, and then hopefully sometimes it does it, sometimes it does not. Like here, you can't do it all at once, but if it's a continuous section like here, then you'll see there's a little exclamation mark that pops up, and you can say convert to number. And unfortunately, it'll have to be section by section. Usually, so this demonstration was a little bit gekookt, for lack of an English word. So in this specific instance, not all of them converted, only some of them converted to number, but usually all of them or none of them convert. And then you can select and just address the exclamation mark. Okay, I just want to make things a little bit neater. Okay, so we've fixed the decimal and we've set to number all the text. Now we need to check that the data is actually accurate, right? So what I do usually here is I take all my IDs, right? And I just put them down here. I want to, so these are still formulas. So let's just paste them as numbers. And then I repeat the column, right? And then I use something in the, no, I can't see. So over here, you've got data, and then under data, look for something called remove duplicates, right? So we remove duplicates. You can say continue with the current section because we've got a very specific aim here. And then say I've got headers, and say okay. Right, so here you can see these are the unique time points. Now, I know the study, and I know that there are only 2 time points. So this is an error, which would have been very difficult to pick up in this setting. So that's why we split, and that's why we count. So this is a problem, right? Let's do the same here. Sorry, this display thingy from Zoom that's popping up. Okay, and we've got 4 subjects. Okay, so now again, from the study design that I'm familiar with, I know that there might be a problem here somewhere, right? So I was not expecting to find a T4, but this seems all right. So we know something's up somewhere. So, okay, let's now go back to the IDs. These ones over here. We do exactly the same. And remove duplicates. So this seems very tedious, but let me tell you, if you don't do this, it's a bit of a problem. Okay, so we know there's no duplicates here. Okay, so we're happy with that, we're happy with this. So this is where the problem lies. So I'm doing this very, obviously this is a small data set, you can spot the problem with your eyes, but just using your eyes, but if you've got large data sets, then that's not possible. So what do we do now? We try to identify the problem. We say count. We say count if this range is equal to this specific criteria. And we fill down. Okay, so we see that time 1 is correct, but somewhere there's a time 2 that's labeled incorrectly. Okay, so you would go and find a T4. So you say Control F, and I want to find T4. You see, okay, so again, you can do this obviously in the small data set just by looking at the data, but I'm doing this more extravagantly. So you see that this is the problem, and here you can see what happened was that the ID number and the sample number, the subject number and the time number was reversed. So this needs to be corrected. This should be subject 4 time 2. Okay, and now everything should be fine. So this is the kind of basic checks and balances that I do. Okay, so we see that this one should be subject 4 time 2. Okay, corrected. So we've done that. Now let's set our missings, look at our missings, set our zeros to missing. Okay, so this was necessary for Metabo Analyst. Metabo Analyst did not see a 0 value as a missing value. It saw it as a 0 and used it mathematically then as a 0. it does not do so anymore, which to me is also a bit of a problem, because sometimes you do have zeros and sometimes you have missing, but okay, that's set aside. Let's say we assume that all these zeros are actually not detected, so they should be missing. So what I would do is I would go to Home tab, and then you would go to, go to Special, and then you can say, no, which one is it? No, it's just the find replace. Sorry, I'm making myself confused here. Okay, so if you go to place, and what you want, oh, this is the trick, sorry, I forgot of it. Okay, so if you want to find your zeros, then you want to replace them with missing, which is just nothing. There's just nothing in that cell over there. That's fine. But now, this can be a problem if you've got zeros that are in your numbers. This can sometimes lead to problems. So it's very important that you go to options, and then you select something called match entire cell content. So the entire cell must be just 0. It doesn't apply to cells that have 0.001 or something like that. You must match the entire cell content. Okay, and then say replace all. So now we've got all our missings filled in, and now I want to count the missings. Just so if you've used Untitled Analyst, you'll know that there's this little information bit that says what percentage of the data was missing. So it's very important for me to check that, because I want to check that all the numbers that I do have, all the data that I do have, was correctly uploaded into Metabolomics Analyst, and I didn't lose any information. So I use something called count blank, and I just select everything. And there you can see there are 25 cells that had missing values. Okay, and you can use this to double check Excel. Right, I can show you how to. Okay, then sorry. The other thing that I usually do is to replace these complicated headers with like special characters that are sometimes an issue, like the semicolon that was used here. I replaced that with a reference list for variables. So I would do the following. So I can copy this. And then I would transpose, right? And then I would rename it to variable 1 all the way through to variable 6, okay? And then these ones I would copy again and transpose back over here. And those are my new variable names, and this is the reference list that I will use going forward. So whatever variable pops up in the stats analysis or the results that are important, I can come back to this list and see what it actually was. So some software packages don't mind the use of these complicated names, others will give you a lot of grief. So depending on what you're going to use, this is a good option. But like I said in the slideshow, do this before you start removing variables, because you want your original, you almost want to do this iteratively, so that you've got data sets for each iteration that you've made changes on, so that you know exactly what steps did what. And specifically here, before you start removing or moving or whatever your variables, rename them immediately and then keep the list, the reference list as is. Okay, and that's it. How are we on time?
Perfect timing. Thank you, Dr. Marie. It is 11 a.m. Are there any questions? I don't see any in the chat. Perhaps there's people who would like to unmute and perhaps ask a question. Can I just get an indication? You can thumbs up for especially people who are new to metabolomics. Was this easy enough to follow? You will then also have access to the presentation through our YouTube channel, and you can go back and revisit some of the concepts covered as well. Okay, Dylan says definitely. So I think it is quite useful. Well, we do still have Dr. Marie scheduled for a follow-up session from 11:15 to 11:45. Tracy Sneyman says, great presentation. So we still have a 30-minute session with Dr. Marie once we come back from our break. So at this point, I'd just like to say thank you, Dr. Marie, for your time. We will take a tea or coffee break. So it is 11 o'clock. We will return at 11:15 sharp. Just take note that during the coffee break, there is a presentation, I think there's a 3-slide presentation that Mulati will post. It is a presentation that will be delivered by, or that's being hosted by LICO. And it's quite interesting given that America is actually celebrating Halloween. I will also post the link in the chat. Make sure to register. I think if you go to that site, the first 250 attendees, there's a little gift pack that you will receive from LICO if you sign up, if you're one of the first 250 people to actually attend. There's a little gift package for you. So it does look like an interesting talk, specifically how metabolomics is changing how we monitor our health, what mass spectrometry can actually tell us about mummies. And then, of course, looking at what it can tell us about death, decomposition, and dogs. So quite interesting. So we will leave the slide floating for a while, but feel free then to get your coffee or your tea, and we will resume at 11:15. Thank you. Okay, so welcome back, everybody. It is 11:15. Hopefully you were able to stretch the legs a little bit and grab a cup of coffee or tea. So we are going to continue with Dr. Marie on the validation of metabolomics data. Are there any questions before we continue? Perhaps something you thought of during the break? I don't see anything in the chat at the moment, Marie. Just great presentation. Very insightful. So just comments. Thank you very much. This was very informative. So I guess if there are no questions, you can then continue with the rest of the presentation, Marie. Just a note to our COD. After Dr. Marie has presented, we will have some fellows presenting again to us. So just a reminder to please complete those evaluation forms. And then just a special thank you again to Metabolomics South Africa, COD, the subcommittees, as well as ACGT, DIPLOMICS, as well as our sponsors, LICO, Microstep. We also have biocreds as well as separations. And then, of course, our delegates as well. We also have SciEx as well as Waters and Samachu, who is consistent partners and assisting us with these events. So over to you, Dr. Marie.
Up and running. Okay. Welcome back. Hope you had a good break. Get everything working again. There we go. Okay, so let's continue on to part 2. And in this section, we're going to look at how validation relates more to.
Excuse me, Marie. There's just a little bit of background noise. I'm going to ask delegates to please mute their mics.
Okay.
Thank you.
Okay. Okay, so we're at part 2. And in this part, we going to, sorry, this is the wrong way around. We did this just now. And now we're going to look at sample collection and sample analysis, and specifically experimental design and measurement design, and how you can use that to improve the validity of your findings. Okay, I think a lot has been said on study design in a lot of courses and so forth, so I'm not going to go into too much detail. I just want to highlight some obvious aspects that will likely improve your statistical power, which, as we said at the beginning, is one of the biggest reasons why we struggle with validity. The aim of design boils down to increasing the signal, so turning up the volume, and reducing the noise, which is measurement error and variation that is not of interest to you. So you don't want to look like the cat here. Shane, I think you'll appreciate this. Okay, so how do we turn up the volume? It's always a good idea to try for a few extra samples. If you can, get more samples. The power of an intervention study is almost always greater than that of an observational study. Try to make your groups as homogeneous as possible. So those are basically the three things. Is you want to either have a larger sample size, or have more control, or reduce the actual variability in your groups. So by selecting on the criteria that's not related to your research, you can remove unwanted variation and increase your power. But you have to be careful, because if you have a lot of selection criteria, then you can't really generalize beyond your selection criteria. So there's a give and take here. So first option, bigger sample size, then get rid of all the variation possible, and last resort, more strict selection criteria. Okay, so once you've tried to increase your signal, then we're going to work on the noise. So here are some options. You can make use of a repeated measures design if at all possible, and then randomize always. You can always randomize to some extent, so randomize wherever possible. And then you can incorporate the unwanted variables in your model. So in other words, if you don't want to, let's say, exclude males from your study or females from your study, then you can use a covariate model that brings in gender as if it were one of the factors that you were interested in the study. Okay, let's dive into a little bit more detail. So the first way of reducing variation is to use repeated measures, because that reduces the variation between individuals, because each individual serves as his or her own or its own control. So the pros is that essentially you're no longer just comparing averages of groups, you're comparing the average change between two situations. And this gives you greater power, which of course allows you to get away with a smaller sample size. Unfortunately, if you have to measure individuals, specifically people, more than once, then the admin becomes a lot and the analysis is a little bit more complicated. So instead of doing independent samples t-test, you would have to do a pair samples t-test, so the data management is a little bit more messy. And the usual example is the pre-post, so before treatment, after treatment, the same people, and then you compare the change. Right. The other tool to use is randomization. So you randomize as far as possible. So if, for instance, you think that the province in which an individual lives has an influence, then you make sure that you select individuals from all possible provinces. So that even when you evaluate province and you see that it might have an effect, then all provinces are equally represented in your treatment and control groups or whatever your design may be, and that gives you that reduces that influence of that confounder, because a founder essentially again reduces your power, and in some instances can even bring in bias and you can draw invalid conclusions. So bottom line is, make sure that your confounder is equally represented across all your experimental groups. Okay. The cons of randomization are absolutely none. There are no cons. So you have to do this. It's very important. So the basic example is in the more measurement design side, or when you analyze your samples, you always randomize samples to batches. But in a more structured setting for the experimental side, if you're evaluating lecturers or courses, then you may want to randomize students to lecturers so that there's no pre-selection or pre-assignment bias. So this is just some of the examples of randomization. Then the last one that I'm listing here today to reduce unwanted variation is to use the stats, is to use the actual model. So you build into your model all these confounders that you weren't able to mitigate in some way. So the pro of this is, of course, that your result is a lot more generalizable because you can, there's no exclusion criteria that needs to be accounted for, but it will require a larger sample size. So it is a bit of a give and take. Models are also a little bit more complex because you're using covariate models, and the typical example would be adjusting for age and gender, which the epidemiology guys usually do. Okay, so to bring the message home, how does experimental design, how does that remove validity, or how can it possibly remove validity from your study? So I'm going to bring the concepts of study design and validity together, and to do that, I'm going to walk you through some design fails. So the most obvious fails is probably the lack of a control group. So let's say you're comparing patient samples before and after treatment. Okay, so kudos for using a repeated measures approach, but not sufficient. Okay, you can conclude that the treatment worked, but only to some extent. You can't actually say that the treatment worked. You can only say that the treatment had some effect, an effect of some sort. So there was a change from pre to post, but that doesn't mean that there was any cure. So unless you've got a gold standard method to say the person does no longer have TB, just an example, then you cannot say that the treatment actually worked. So what you would need here is a control group. And if the post-treatment and the control group overlap, then you can say, yes, it looks as if the treatment is working. Okay, so what if a control group is not available and the sampling strategy is limited, right? Then you may not be able to generalize, but there is still hope. Okay, so you have to be honest when you report your findings. So in terms of validation, my advice would be to compare your results to maybe disease or healthy reference ranges, if at all possible. So if your research design does not allow generalization of results, validate your findings from literature as far as possible. In other words, does it make sense? Does it fall within normal reference ranges? Does it make sense in the sense of what's already known about the field? If it really is a bit strange, then your two options are basically to propose future research or further research, or you have to just write it off as an incidental finding that's unlikely to repeat itself. What about measurement design? So how can this put us in a pinch? Well, this deserves a little bit more focus. Measurement design is essentially how you collect data. When it comes to metabolomics, especially untargeted metabolomics, validity becomes a real concern because you're not even 100% sure of your compound ID. You may be thinking like in the joke, you're measuring the magnetic resistance of fish, but actually you're measuring fish head whackability, for lack of a better description. So in my opinion, untargeted work can really only be hypothesis generating. We can't really confirm anything. Only once the IDs have been confirmed can you say that the finding has been validated. So now we've got the design in place. How do we move to a solid collection of data? Measurement design. Okay. To get the most out of your measurement design, the following, in my opinion, has to be in place. There has to be an SOP. The rule is if it's not stopped, stop it. Sorry. So the method you plan to use should preferably be validated when your study involves comparing groups. Ask for a validation report. This will help you understand what kind of variation you start off with. So any analytical method has variability in it inherently. So you have to know what's your starting point. If that's very big, then your measurement instrument might not be appropriate for what you're trying to do. Also look at the bias of the method. So if there's a big bias, then you may not be able to use reported reference ranges or published reference ranges. You may need to use their in-house reference ranges, which might be problematic for publication. You will also know how stable the samples are. So this is kind of important. So usually in a validation report, you'll see that the prepped sample or the auto-sampler stability of the sample within the auto-sampler is, let's say, 12 hours. And this helps you greatly to plan your analysis in such a way that you don't end up with severe drift like we saw in the previous presentation, where you've got QCs all over the show. Okay, if a validation report is not possible, you have to go and ask the experts that use the method in the lab every day so that they can assist you. If you're not comparing two groups, so remember, validation is optional if you're not if you're comparing groups, because whatever is present for the one will be present for the other, and essentially when you start comparing, it will cancel out to some extent. So I'm putting this in quotes, only to some extent. But if you're not comparing groups and your method, then your method must be validated, because none of the variability and none of the bias cancels out. And that means that the raw measures need to be valid, and you can't really, I would be hesitant to use an unvalidated method. Okay. So you get the bias, the imprecision, and the prep stability all from your analytical method. That's information that you need to start planning your batch design. So the core of measurement design is actually the batch content. So what's in the batch and what's the order in which you're going to run it. So first you need to set an acceptable batch size. So the runtime for the last sample is not affected by the sample instability that's known for the method. So for instance, they saw that there was a deterioration in sensitivity after 12 hours. Then you make sure that your batch does not run beyond 12 hours, and that includes the final QC. So the entire batch should be within that time frame, that validated time frame. Next, you need to position your QCs, so they should be positioned at the beginning and the end of the batch always, but then also at appropriate intervals between samples. And you can deduce the intervals. It's a bit subjective, but you can use the imprecision reported for the method. If there's a lot of imprecision, then you want more QCs. If the method is precise, there's no real variability from the method side, then you can use less QC. So for GC, we usually have every 5 to 10 samples of QC. For NMR, for example, we only have one QC somewhere in the middle, because NMR is so much more repeatable. Okay. Now, the QC itself. I want to take a step back here and discuss your options when it comes to QCs. The sample you choose as your QC will determine your ability to assess and correct your measurement error. I almost want to repeat this. If you select the wrong QC, you won't be able to really assess or correct for measurement error. So you should use a single sample as a QC. That's the first thing. It will be prepped multiple times. So aliquot it before you start, please, and make sure you've got enough aliquots. You don't want to, I can never pronounce this, freeze, thaw your QC aliquots at different frequencies throughout your analysis. That's another source of variation that will affect your QCs and won't affect your samples. So it will be to the detriment, to your detriment when you're using QCs to correct your measurement error. All aliquots should be handled exactly the same. So make sure you've got enough volume. Your QC should be representative of the compounds and the biological matrix. So if you don't, a pooled QC is usually preferred, because obviously then everything that's in your study is in your QC. Sometimes that's not possible, but then you have to make sure that at least you've got an idea of that all the compounds that should be in there will be in there. Remember, if a compound is not detected in your QC, you can't assess whether it's of acceptable quality, and you also can't do any corrections if it's not in your QC. All right, and then obviously matrix. If it's in a completely different matrix, then it will respond differently to maybe the prep as well as the analytical part. How the instrument interacts with the matrix is different, and that means that whatever correction or assessment you do is not really valid for your samples. Okay, so pool QC is the best, but watch out if you've got a whole lot of samples that you would have to pool, and you might end up diluting some of the compounds, which is also a problem. So if you've got a large study and you're now going to pool, I don't know, 100 samples to get to your pooled QC, and the compounds of interest you're expecting to be in low concentration, then you're going to have an issue with dilution. So I would maybe then say randomly select individuals from all the groups in your study design, and in that way, everyone is still represented, and your QC has not been diluted away, or the small compounds in your QC has not been diluted away. Okay, I think that's all that I want to say here. Okay, so back to the batch layout or the run order. Except for the positioning of the QCs, your placement of your actual samples should be randomized to the batches. Also randomized in terms of the run order. So you don't want to, in each batch, let's say in each batch you do have controls and treatments, but you always have controls at the front of the batch and treatments at the end of the batch. That's not correct. It has to be randomized in terms of the batch and the run order. Because then you're sure that all that variability is at least spread out equally across your experimental groups. Importantly, each batch should be representative of the design. So all the groups should be represented in all the batches. That's a prerequisite if you want to use MetaboAnalyst to do batch correction. Okay. If possible, I mentioned this earlier, repeat the analysis of some samples so that when you do a QC correction, you can go back to those repeated samples and compare them to each other to see if your QC correction improved the data quality or actually made it worse, because it can happen. QC correction can make things worse. Finally, plan ahead. What are you going to do if you have to repeat samples? Right? So sometimes a sample doesn't inject, sometimes your volume is a little bit, or something went wrong with the prep, or I don't know, the aircon broke and the temperature in the lab was too much and they stood too long in the autosampler and you have to redo stuff. Plan ahead. Can you prep them again? Is there enough sample to do that? Can you re-inject them directly at the end of the batch again? Would that be okay? Do you need to sleep next to the instrument to make sure nothing goes wrong? Okay, so especially if you think some of the samples may be problematic, you may want to sleep next to the instrument for the time running. Then importantly, sometimes people forget this, if you're going to add to the batch, remember to also add QCs again as you add to the end of your batch, so that you've got QCs all the way through to the very end of the batch. Okay, so here's an example of a standard GC batch layout that we've got. We have some junk QC samples always at the beginning. That's just to condition the column. We'll discard them. But then we also have leading QCs and trailing QCs at the beginning and the end of each batch. And then every fifth sample, because this specific instrument is known to be sensitive to drifts. So we've added QCs quite frequently. Then in terms of the experimental design, in this example, we've got 20 controls and 30 treated samples. So our SOP says no more than 20 runs per batch. It's about 60 minutes a run, so a little bit over. So we don't want to exceed 24 hours. That's been a problem in the past. So we need to spread the samples in a random but representative manner across the slots. So the order I presented here is hopefully a good measurement design. So you can see all the controls and all the treatments controls and treatments are represented in all the batches, and then they are randomized. And you can see there's some basic calculations that you can do to help. You can look at this in a little bit more detail if you want. Okay. So lastly, what is an example of a measurement design fail? So let's say you can use what's left of some lab consumables for free, right? Great, bargain, get free consumables. But only if you analyze your samples now. If you wait, you'll have to order double for your own account. So in your pre-post design, you may already have all your pre-samples. So now you may be tempted to run all your pre-samples on the free consumables, right? Don't. Okay. Also, you don't have a control group, but there is data available on healthy control samples. So what do? Well, firstly, you don't save money, okay? If you run whatever samples you already have, you're most likely the pre-cases, and you use the control study, your data is not valid. Why? Because basically you're measuring differences between batches and not differences between your groups. And this seems very obvious, but I've seen desperate times and I've seen people cling to straws, and then you end up with something that looks really promising, because yes, batch 20 and batch 1 differs a lot, and batch 21 and batch 1 may not differ a lot, but it's completely invalid, the results of such design. Okay, so I think that's about what I wanted to cover. Maybe I can wait, Relia, do you want to go for questions first, and then I can maybe show one more video?
Yeah, that's fine. So I don't have a question. I just have, I think it's a comment from Prof. Duncan Cromartie. Pooling could in fact show the differences easier due to diluting out the analyte of interest for the pool versus the samples, where the same analyte is in fact in low but minimally changed concentration. Okay. Would you like me to read that again, or are you able to view it?
I think I've got it. I'm not 100% sure. So essentially, the effect of dilution can go both ways. Is that how? So it can.
Yeah. I think it's just a comment from Prof. Duncan.
Well. Yeah.
If you'd like to unmute. So I think it's more of a comment where he's just stating that pooling could in fact highlight the differences easier.
Can you hear me now?
Yes, I can.
Good. When you've got very small changes in a particular analyte, whether it's changing either by increasing or decreasing, very often you only pick that up if you have pooled everything from your sample. So if you pool from every single one of your subjects and you create a single pool that you use as a, call it a QC or a reference library, whatever you want, then it's often easier to find those that are showing minimal change. If you start selecting, you may find that you are not seeing those small subtle changes. That's something that we've picked up.
Yeah. So I think that makes sense to me, in the sense that if you're expecting if it's in very low quantities and you might miss it, then then you pool basically according to your study design, if I understand correctly. So you would pool all your cases and pool all your controls, and then look for something that might just be in very small quantity to inflate that signal. But I think then you have to be sure of the compound. Then that would make sense to me, because the quality control is kind of beforehand. So if it depends a little bit on how the analysis was done, but yes, I understand your point. So in some instances, pooling does inflate the signal, which is a good thing, but you have to tread carefully and keep in mind what you're trying to achieve with your pooling strategy.
Can I just ask, for someone who is sort of new to metabolomics, Dr. Marie, so if, let's say, I have 10 samples and I need to pool these to form a QC, if I use, let's say, 50 microliters for my extraction of the actual sample, do I then take 50 microliters of each of those samples for the QC, or does it not matter as long as you take equal volumes to form that pool? So if you extract, let's say you use a sample that's 50 microliters, can the volume that I take for the QC be 20 microliters from each sample, or should it also be 50 microliters?
So that would depend on the number of QCs you need to run. So you need to work out how many QC samples you're going to need, what is the prep volume for each of those aliquots, basically, and then you reverse engineer what volume. So it might not be related at all. You may need like 1 microliter from each if you've got a lot, even though the prep volume is more than that, just simply because you're not interested in, you're interested in one sample that can be aliquoted into sufficient smaller samples. Does that answer kind of the question? What I do want to mention just is urine. I'm not always sure how the whole creatinine thing is brought into pooling QCs, and whether you should then have variable volumes based on the creatinine of the different samples. So that's something that makes it even more complicated.
Yeah, with urine, it's a little bit different. Daniel has a comment or question here. He says, sometimes I get very large standard deviations within groups, even after standardization and scaling. Which is the best way to handle such data set?
Welcome. Welcome to my world. Yeah, and there's not much you can do. If you've got large variation, you've got large variation. You could try to split out the different sources of variation. So if you know that there are different collection sites or something that you haven't brought into your analysis yet, if you're just looking at your groups of interest, but there's actually some other variables that may be influential, then you can bring those in to try to kind of split off the variability and zoom in on the variability that you're actually interested in. Yeah, I've seen people kind of pair individuals, so maybe you pair individuals of within a 1 year age, 2 year age range from each other, and same genders, same as far as possible. I don't like that. I think, well, depending on what you're trying to do, but I think most journals will probably be a little bit uncomfortable. But there's really not much you can do. Scaling is not going to save you from a large standard deviation, unfortunately.
Okay. Are there any other questions?
I see Prof. Duncan's hand is up.
Prof. Duncan, you can go ahead and...
No, just going back to the pooling, as long as you pool the same amount from every individual or sample or whatever that is put into it, it should always be the same amount, so that you're not biasing the pool through some coincidental change that's there.
Yes, so
just to comment on the large standard deviation, if you can relate it back to the standard deviation you're finding from your control samples, it's going to give you some idea of your expected technical variance versus the biological variance that's going to come from your sample. So biological samples are always much higher variability, and that quite often we cannot control for. So you need to take the biological differences as being some kind of variation that you wouldn't have expected to find if you were analyzing the same sample over and over. But if it's falling close to your technical variance, then you're already sitting with a clear indication that it's not change based purely on the methodology. So you've got to be careful with that.
Okay. There's also a comment, I think it still relates to the standard deviation aspect. That's from Dr. Shane Mason. It says, use internal standards at different points of your experiment to pinpoint where variation lies in your design.
Okay. Yeah, I'm not 100% sure what he means there. So I know in the past we've used like a single internal standard, and we've been critiqued on that. So I'm not sure if it relates to the same thing, but you do want internal standards popping up throughout your run. You don't want just a single one that only represents a single, can I say, point in time during one analysis. So I think that's what he's meaning.
Okay. Dr. Mason, did you want to comment on that or just clarify? Okay, Daniel says, thank you, Maria and Shane. Prof. Ian Dubry says, thank you, Maria, good overview of the important basics. Okay, I don't see any other questions at this point, Marie, and I don't see any hands up. Perhaps you can go ahead and show us the video that you wanted to. Do you have an idea of how long it is?
No, it's short.
One. Yeah, okay. All right. Then I'll just allow you a few more minutes then.
Sorry, let me just share my screen first, and that will help. Okay, so this is pre-recorded, so it goes quicker usually. Okay, can you see the Excel?
Yes, I can.
Okay. Why is it not playing? Sorry, guys. Let me do it this way.
I don't think the sound is that clear.
Is it not working?
Mm-mm.
Okay, I'm gonna mute it, and then I'm just going to play the video, and I'll talk you through it.
So just
Okay.
before the share button there, before you share the screen, there's a box you have to tick at the bottom that says allow audio.
Oh, I see. Okay. Okay, let's try again. Thanks, Lottie. Share sound. Thank you. That's great. Okay. Let's try again. Okay, so just to where this comes in is when you're correcting for multiple testing. So I know Metaboanalyst does this, but if for some reason you need to do it on your own, you can do it in Excel rather simply. And so the first part of the video explains why you need to correct for multiple testing, and the second part shows you how. Oh, okay. Oh.
Two, and they've got the same.
Sorry. Okay, there we go.
Got two populations, group 1 and group 2, and they've got the
We're
same
seeing your
mean,
other screen now.
both a mean of 2.
With-
Okay,
Yeah,
so what I'm doing is essentially every time I click in here.
What screen are you seeing?
The one with the
With the?
with the folder.
Oh, jeez. Ah,
There we go.
okay. Let's try
There
again.
we go.
Got two populations, group 1 and group 2, and they've got the same means, both a mean of 2. Okay, so what I'm doing is essentially every time I click in here, then the sample is regenerated, right? And I've coded a t-test into this cell over here to show you the p-value. So this is the p-value from a t-test. And this is the kind of p-value that you would expect because you've got two groups with equal means. So the p-value should be large. There should be little to no chance that by random sampling, you can get a difference that's big enough to be considered important. But watch what happens if I keep on doing this. P-value of 0.1. It dropped from 0.9 to 0.1. Let's keep going. Okay, here we go. It didn't take me too long to get to a p-value that's significant, just by repeating and repeating and repeating the sampling, or repeating and repeating and repeating the test. So how this works is very basic. You've got your p-values generated through your multiple tests. So here we've done a total of 8 tests, and I've got my 8 p-values here as well. So I've sorted my p-values from the smallest p-value to the largest p-value. And now I'm just saying, well, if it's smaller than 0.05, which is my alpha over here, then I'm happy to say that we've got a significant result, something that might be or likely to be found again if we were to resample, or is likely to be true for the population. Right, so I've got a couple of, almost all of my tests except the last one were significant. Okay, then I've assigned a rank. So this is just my top p-value, my smallest p-value, to my largest p-value for my 8 tests. Now I need to adjust the p-value. So I'm going to make changes to my actual p-value, and this is now the p-value that I'm going to use to make decisions on. So how do I do this? I use the formula provided here. So I take my original p-value and I times it by this factor over here, which is the number of tests, which is 8, minus the rank of the current test, which is this value over here, plus 1. So here's my formula. I'm taking the current p-value, p1, I'm timesing it by the count. This is the number of tests performed. Now I could have just placed 8 here or taken the maximum of a year. There's a couple of formulas. I'm just trying to show you some more and more functions in Excel as well. So this would be 8, and I'm minusing the rank, I'm subtracting the rank, and then +1 to complete the formula. So enter. My new p-value is now 0.01. So I've changed from 0.001 to 0.01. And I continue to do so up until the very end. And now can you see that originally we had almost 7 significant results, and now we only have 2. And this is done in order to make sure that this 5% stays 5% and doesn't end up being 15 or 20% without us realizing it.
Okay, that's it from my side.
Thank you so much, Dr. Marie. I'm just going to double check and make sure I don't see any questions. Prof. Zeno Apostolidis says, thank you, Dr. van Wyk, 2 excellent presentations. So if there are no further questions, we will move over to our next speaker. Thank you so much, Dr. Marie.
Thank you for having me.
Feel free to please post your email address in the chat room in case there are any specific questions from individuals. Thank you so much.